Hello again, everyone. This is part 2 of SI units and orders of magnitude. And we're discussing this, of course, because scientists need to be sure that they are using the same units as everyone else and that all the units mean the same things to different people. We're not going to talk about SI units very much this time, but we are going to talk about another way to use orders of magnitude. And that way is standard form. Standard form is also called scientific notation. A notation is a way of noting things, of making notes. And standard form is another way for scientists to record very big numbers or very small numbers. It's a different way to use orders of magnitude. So the good news is you need to remember less to learn standard form. There are no long lists of names, but the bad news is there's a little bit more maths to be done. You have to think a little bit mathematically. So let's look at an example. Here's a very large number, 314 million. It's a pretty big number. But how would we write the same number in standard form? Well, this is how. 3.14 times 10 to the 8. So what have we done there? Well, we use a number that's less than 10 and more than 1, or equal to 1. And you will see some people using numbers that are greater than 10. You can use standard form that way, as you will see, but for the best way to do it, you try and get your number to between 1 and 10. And then we multiply that by some power of 10. 10 to the power of 8 in this example. So that's 10 times 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 10. 10 to the power of 8. So how do we find this other number? Where does the 8 come from, in fact? Well, step 1, we need to make that number from 1 to 10. So if we take our big number, the first thing we need to do is chop off the zeros at the end. Cut off all the zeros that we don't need, and then we have a smaller number, 314. But that is not small enough. We need to add a decimal point to make it a number from 1 to 10. We have a small number with the same digits as our original big number. But what have we just done mathematically? Well, what we've done is change the orders of magnitude. And how did we do that? Step 2, how many orders of magnitude are there between the big and the small numbers? Well, if we start with our original number, 314 million, and we add a decimal point by putting 0.0 on the end. Now, to make our small number, we need to move the decimal point to here, between the 3 and the 1. So how many places do we need to move it? Well, let's look. 1, 2, 3, 4, 5, 6, 7, 8. 8 places to the left. So to make our small number from our big number, we need to move our decimal point 8 digits to the left. And if we look at our standard form, 3.14 times 10 to the 8. This is where our 8 comes from. So it's fairly straightforward, in fact. We can do this with small numbers as well. It's the same, only we have to move our decimal point to the right. So if we look at this very small number, 0.000000314, how would we write this number out in standard form? Well, if you look, you'll find it is almost exactly the same. 3.14 times 10 to the minus 8, negative 8. So when we move the decimal point to the right, we use a negative power. And a little word of warning, you will notice you have to move it 1 point further than the number of zeros you have. So in our small number there are only 7 zeros, but if we stop after -7, then we have 0.3, and that is not big enough. We need our number between 1 and 10, so we have to go 1 place further to go over the 3, and that means we have 3.14 times 10 to the -8. So why do we need standard form? You might be thinking that we don't need standard form. If you look at the two numbers that we had, the big numbers and the standard form version, 314 million and 3.14 times 10 to the 8, well, it's not very different to write either A or B, is it? Right? But if we look at some other scientific constants, we will see why standard form is still useful. So don't worry about what these constants are, just worry about the numbers, the size of the numbers. So the Bohr radius of a hydrogen atom is 5.29 times 10 to the minus 11 meters. The Hartree energy is 4.36 times 10 to the minus 18 joules. Avogadro's constant is 6.022 times 10 to the minus 23 moles to the minus 1. The diameter of the observed universe, a big number there, is 9.3 times 10 to the 26 meters. The mass of an electron is 9.11 times 10 to the minus 31 kilograms. And the Planck constant is 6.626 times 10 to the minus 34 joule seconds. So most of those are very small numbers, but there are plenty of very, very big numbers that we could use as well. And if you want to see orders of magnitude and standard form in action, have a look at scaleofuniverse.com. It's a very useful little web application which will show you exactly how big or small you are, and you can see all of the very biggest things and the very smallest things in the universe. But for us, that is where we will stop. So that comes to the end of our little talk about standard form and orders of magnitude. I hope you found it useful, and until next time, bye bye.